Well, I think I'll start. This is, in fact, ECE 4760. You can easily Google ECE 4760. The top hit should be this class. We're also on video note, where the lectures are being recorded, and last year's video note lectures are all on YouTube at 4760. Search term. There's also about 250 student project videos on the YouTube channel, of which about 60 are done with PIC 32, and the rest are the old AVR architecture. So there's a fair amount of online material that you're going to want to look at as the semester goes on to figure out how the course operates. My office is 214 Phillips. You probably already figured that out. Stop by anytime. My primary job this semester is to help people with this course. That's what I'm hired to do. And you're welcome to stop by anytime and talk. I will mostly have time to talk. Every once in a while I'll be in mode panic because I haven't written a lecture or something of the sort, and I won't be able to talk, but usually I can. This Friday, you know what's happening this Friday on campus? Inauguration. And a fellow that I work with, Joe Scavira, and I volunteered to set up a booth at the inauguration to show everybody what ECE does, whatever that is. And so we've got lots of flashing lights and microcontrollers and stuff. But so before class on Friday for 2 hours, I'm going to be setting up. And then I'll be here at noon, hopefully, to talk to you. And then sometime just before 1, I'll be going back over there to finish setup. And probably Friday I won't have much time to talk. But aside from that, I'll have time to talk. You should have all gotten a message. You should have all gotten a Piazza notification. Anybody not get one? So there's a Piazza group set up. I would appreciate it if you route general questions through Piazza. You can post anonymously. We get some economy of scale that way. On the other hand, I'm also happy to talk in person. You can Google me at Bruce Land. Should be able to get the top hit there. The course webpage has all of the gory details. But let's scroll down to the section that talks about staff. If I can remember how to use this primitive device that doesn't have a touch screen. Oh, it doesn't. Oh, let's see. I can do Shift plus or something on here, I guess, or Command plus and zoom in. Yes, that's right. That's the sad state of affairs. So the TAs this year are two Brians, Brian Clark and Brian Gross, Samir Durvasula, Sean Shetty, and Mark Zhao. And the assignments for them are under the TA assignments. They will also be consulting. So in lab, we will have double coverage in the sense that there will be a TA that's assigned to your section and who will evaluate you. And there will be a second TA who will be there to help answer questions. And on Wednesday, Thursday, and Friday afternoons, I'll be in lab also. I'm not going to be in the 4:30 to 7:30 sections because my stamina isn't good enough. Besides, I like being married. And so everything's there's a certain amount of compromise. In the schedule section, there's also a layout of due dates for projects. Week 0. We're zero based here. That's like today. If you want to come in and start building a board, we can have about 6 or 7 people at a time work on soldering. There'll be a little bit of surface mount, some through-hole soldering, but don't bother to sit down at the soldering until you have read the document which describes how to build the boards. Next 2 weeks will be Lab 1. At the end of week 2 of Lab 1, you will demo, which will be 30% of your lab grade. So week 2, if let's say you have a Tuesday lab, week 2 on Tuesday, you demo. The very next day, on Wednesday, Lab 2 starts. All right, there is no downtime. The very next day Lab 2 starts. You have 2 weeks to work on that, and then another demo. Lab 3 goes 3 weeks because it's a monster. Not only are you going to generate a video game, but you have to figure out how to use direct memory access coprocessor to make sound effects. So you're going to want to paw through this schedule and make sure you keep track of the deadlines. All of the reading is here, broken down by lab. Lab 1, Lab 2, so on. And you really need to start on the Lab 1 reading 2 days ago. There is a lot of detail which we will plow through concerning the packaging, the peripherals, and of course programming. If I had to characterize this course in a sentence or two, this is sort of like the elevator pitch for the course. It's hardware, software, co-design with an emphasis on hardware concurrency. So you learned about software concurrency in 3140, how you make a scheduler, how you do task swapping, how you coordinate variables, semaphores, a locking of regions of memory and other resources. What we're going to talk about in this class is how do you get good performance out of a fairly small processor by using the dozens of peripherals that exist on the chip. For instance, there's timers. Every timer is a small coprocessor that has a very limited instruction set. It knows how to increment, it knows how to compare, and it knows how to toggle certain I/O pins. There are much more sophisticated peripherals on this chip, including serializers and deserializers of various sorts, but also so-called direct memory access peripheral, which is a bus master just like the CPU. It can issue bus commands just like the CPU. It can make decisions about the data that's passing through it, and it can do all kinds of copying operations on a separate memory channel than the CPU, because the memory is not a bus, it is a crossbar. There are 5 sources and at least 3 targets for memory addresses, and so you can do several memory accesses at the same time, depending. So some of you will say, you have a processor that can copy memory and make decisions. That sounds like a Turing machine. I think it's an open question. I believe that the DMA channels are compute universal. I haven't proved it. Could make a good final project if you're sort of CS-y. We'd like people to work together in groups of 2 or 3. If you absolutely can't stand it, you can work by yourself. I do not recommend it. Groups of more than 3 I won't allow for the first part of the course. Maybe for a final project you can work in a larger group if you scale the work. So the first 4 projects that we're going to do, I'll talk about in a minute, the work doesn't scale very well, so I want the group size to be constant. For the final project, you have double the number of people, you do double the amount of work. But again, I would say any group greater than 4 would have to have very good reasons. I've had one group of 5 once in 20 years. One guy did nothing. That's a problem with groups of 5. He also got graded down 20 points on the final project. Typically, project courses are more work than test and homework courses. So I don't recommend, if any of you are doing this, stop doing it. Don't take more than 2 project courses during a semester. It's bad for your brain. 2 weeks of 4 hours of sleep or less a night will take any of you healthy 20-year-olds and turn you pre-diabetic. All right? Don't do it. Or at least try not to. There is no text. There's a ton of stuff online. We'll do everything we can to help you learn it, but you're going to have to do some upfront reading to get into the system. Any questions?
When are we forming our groups?
You could walk into lab with a group already in mind, otherwise in lab. It's student selected. I don't enforce groups. And there is no limitation. You can change group members at any time. We ask you to don't change in the middle of a lab. But at the end of a lab, if you want to change groups, you can do that. The TAs just love the paperwork. There's 3 basic documents you're going to be looking at through the semester. There is the PIC hardware manual, and the entire manual is available. It is huge. Download it if you're masochistic. I downloaded the sections which you're going to want to start with I/O ports and timers. This describes the hardware structure, the programming model of the hardware. In other words, what the registers do, what the hardware registers do, how the timers work, how the I/O pins work. The I/O pins are a very significantly complicated peripheral on this chip. You're going to want to read that real soon. The second thing you're going to be using all semester is the peripheral libraries, plib. There's a fairly good description in PDF form. There's also embedded help in MPLab X, which is the IDE you're going to be using. You can download that to your own laptop and it works just as well. We're using the unlicensed version. Unlicensed version will do level 1 optimization, but not level 2 or 3 in the GCC sense, right? GCC optimization levels. You can optionally enable a 30-day license for the full version with full optimization. I suggest not doing that for Lab 1. Do that for the final project. Okay. So you're going to be flipping back and forth between the hardware manual, which describes the hardware, and the peripheral libraries, which describes the software that touches the hardware, that deals with the hardware. And the third thing you're going to need to look at is the PIC32 data sheet, MX2 data sheet, mostly for electrical and temperature requirements. Remember, this is partly an analog course. And you're going to have to worry about voltage levels. You're going to have to worry about noise immunity. You're going to have to worry about crosstalk between analog and digital channels. And so you're going to have to know something electrically about the chip. Thevenin input, Thevenin output, equivalent resistances. For that, you need the data sheet. And nobody ever reads the hardware, the Tektronix manuals, but we do have one linked up. If you want to learn how to use an oscilloscope, you could read the manual and also the signal generator, but nobody ever does. But you do need to read the policy page, because this is the implicit contract that you are signing by taking this course. This says what you will do. 3140, your permission, reading, blah, 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 purpose, read it up. It's a design course. We're not going to give you all the answers. We're going to help you get to the answers as much as we can. But cleverness, ingenuity matter. Right? Think about the problems. The meat of the matter here, though, is grading. 50% is going to be on homework, on laboratory assignments, 50% on the final project. There are no tests. There's no other evaluation except what you do in lab. Do you come to lab ready to work? In other words, have you read the material? Have you thought about the code? How efficient are you? How good is the result? Does it meet all the specifications given in the lab write-up? And how well do you write it up? 50% of the grade is the write-up. Yeah, okay. As usual, a late demo receives a 0 grade, with exceptions, of course, for health and family emergencies. But you need to be prepared. It means doing the homework. It means doing the reading. You have to perform. And that's it. 50% final project is a lot of fun, because there's a lot of creativity involved. You get to work on a project that you care about, that you specify, with some limitations. No weapons, no rail guns, nothing that can be construed as a weapon or a projectile launcher. No automatic ping pong ball throwers. Testing them in lab is just a nightmare. And no drug or alcohol related devices of any sort, unless they're explicitly approved. For instance, a breathalyzer might be approved. But you're going to improve a vaping unit? So we reserve the right to differentially grade members of a group if we observe differential performance. And of course, there's a regrade policy, but we would like you to ask for regrades within a week, because as the semester rolls on, except for egregious addition errors, of course, but as the semester rolls on, the TAs forget the details of exactly how they graded a given paragraph, and so to be fair to them, you have to ask for a regrade within a reasonable amount of time. We expect you all to abide by the Code of Academic Integrity and Cornell's policy on equal education and employment opportunity. There's a section on lab reports which gives an outline of what I want in the report, and has some examples. An example report. Oh, which isn't found. Oh, great. I better go edit that. How about that one? It's connecting to nothing. Oh, good. All right, I'll fix that. I'm sure glad I tested that in front of you. And, of course, any academic concerns you have, come talk to engineering advising. But read this. Seriously, read it. And come back with any questions next time. I tried to simplify a few things. There is a PIC 32 MX250 full pinout, which comes directly out of the hardware manual. You look at that thing, you say, I have no idea what that's saying. I can't parse that mess. So I rewrote it in a tasteful monofont here, which has all of the possible signal names, and you're gonna look at this a lot. There's a stripped down version that a student made last year, which is not complete, but is much more colorful because it looks like an Arduino layout. Has lots of omissions. There's pieces missing, but what it has is easy to understand. So you can use any of these, but in the end you may well default back to the full version for some details. Let's talk about lab assignments. First thing you're going to do is you don't have to construct the board right off. I would suggest constructing a board. You don't have to. We're going to have you build a capacitance meter. You put in a capacitance. The liquid crystal display gives you the value in nanofarads. What you're going to find is if you spend the time, which will be about an hour and a half or so, depending on your soldering skills, to build a board, that you will save a ton of debugging time. So, because if you build the target board, then you will not have to wire a TFT or the DAC to the CPU ever again. Otherwise, you'll be wiring that for every lab. So sometime in the next 2 or 3 weeks, you're going to want to construct the board, build a capacitance meter. There's a minimum amount of circuitry here. This shows the MicroStick 2, which is a board you don't have to build. If you just want to walk in and pick up the hardware and start using it because you're allergic to solder. Anybody allergic to solder? By the way, this is full lead solder, folks. This is the real toxic material. In other words, after you solder, don't rub your eyes until you wash your hands. It'll hurt. Lead ions in the eyes hurt. All right, so if you don't want to solder, you can always use MicroStick 2. It's fine. There's a few details on how to wire it up. There's a suggested wiring diagram, a suggested pin use list here. However, my guess is that most of you are going to build a board and use the MicroStick 2 as a programmer for your target board. And I believe I linked, oh yes, there's the picture of the lovely target board. Can you see that against the glare of the overheads? Yeah, good enough. So, CPU, port expander, because there's only 27 pins on this device. This adds another 16 I/O lines. TFT, full color 320 by 240 display. Right down, nestled under the programming lines here is a 12-bit stereo DAC, power supply, expansion connector. you're probably going to want to build that. Any questions about that, about Lab 1? Capacitance meter. It's all about timing. Yes?
Some of the documentation mentions both the small board and the large board. Are there two of them you can build?
You will build one or the other. I suggest building the large board. It's more work to build, but you have less debugging to do thereafter. The small board is designed for when you want to take a CPU and throw it into your final project design. It's a board, it's stripped down, there's nothing on the board except the CPU, an I/O header, and a power supply. I expect we'll see those boards built into everything because they're cheap and easy to build, but they're designed for final projects as opposed for the ongoing projects during the semester. If you build a small board, it's yours. You can keep it. If you build a big board, it's yours, except for the TFT display, which I need back, because they're 25 bucks a pop. Second lab will be a cricket call generator. Cricket calls are structured sine waves. And so at a very fine grain, you have a sine wave burst. It has to be modulated smoothly. Otherwise, the Fourier components include high frequency clicks, which are annoying to the grader's ear. Those are going to be structured into groups, which will then be structured into groups. So you'll have a hierarchically organized sine wave generator. So the theory here is direct digital synthesis. How do you build a sine wave on a cheap little computer that you can output at 44 kilohertz for audio quality? The peripherals we'll be using are serial peripheral interface to drive the DAC, that is a serializer. SPI is a high-speed serializer for outputting serial data, and a timer which will do the high-speed synthesis. In other words, it will produce 22 microsecond precision intervals for doing the sampling for the direct digital synthesis. And really a lot of the course has to do with precision timing. Third lab will be a video game, which I don't think you can find code for anywhere because I invented it. It's not to say it's wonderful, but it is obscure. And so there's hardball dynamics. You got to do a little bit of vector calculus here, a little bit of vector arithmetic. This is, after all, this is a culminating design experience course. I can draw on your physics for this course. It's legal. All right, so this is a physics simulation of colliding spheres. And it's evil enough that I actually gave you some pseudocode here because it took a while to figure it out. But let me show you one of the demos of a similar game. What do I want to do? Oh, it's a movie? MOV? What? Okay, let's try QuickTime and see what happens. Okay, balls flying all over the place doing who knows what. And the interesting thing here is that the way we're grading this is by the number of balls you can animate. And that means this is performance-based. You have to have efficient code. It has to execute quickly. That means fixed point arithmetic, no floating point. So you have to use fixed point arithmetic, and to do the sound effects, you could use as much as 25% of the CPU unless you use direct memory access. In other words, you use this high-powered coprocessor for doing the sound. And so this forces you to learn DMA. And there's a huge specification here because it's an ugly big program, but Lab 4 is brand new this semester. You know what that means, right? New lab. Guess who the guinea pigs are? So I tested it a lot during the semester. I have reason to believe it actually works, but that's, you know,
of design videos for a new lab.
so this is about a 12-inch long balsa wood beam with a motor on the end, and a little tiny prop.
Adding a large derivative term and increasing the
And
a little bit so that the response
God, this guy is
better.
boring.
And the on the microcontroller system is commanded to come to horizontal, then to plus 30 degrees, then minus 30 degrees, then back to horizontal.
Now you're going to build that arm and all of the stuff that goes with it. And I just can't wait to hear what the TAs have to say about 25 of these running at 10,000 RPM in the lab. It is going to sound like a room full of mosquitoes. For safety, I did the experiment. I revved this thing up to 12,000 RPM. I overvoltaged it. I stuck my finger into the prop. And you know what? It hurt. It didn't cut me. And so I think it's safe enough. Now, you don't want to run it into your face. And there's a nonlinearity here. You got this thing that comes up. It's a lever arm. Once it gets past horizontal, as it comes up like this, the differential torque required to pull it further goes lower and lower until it's zero when it's vertical. And so once it starts past the neutral position, it goes whomp and crashes into the table or your arm or whatever happens to be there. So not only do you have to think about control, you have to think about safety. How are you going to limit this thing so that it can't go much above 45 degrees? It should bang into a stop. You should engineer in a stop into it, which I didn't do, and then ran it into my face and my desk and the power supply leads and everything else, because I know what I'm doing. And this was entertaining. I had a lot of fun building this semester. The angle sensor is going to be a potentiometer. It's a special low torque potentiometer. You got to signal condition it just a little bit, send it in the microcontroller. There's a fair amount of circuitry for the motor drive because it's got to be opto-isolated to avoid spike feedback from the motor. So there's going to be some hardware here, and I tried to write a little simulator, which I think might be useful, or maybe not. But that should be entertaining. And then, of course, the design project. We will ask you to write a one-page proposal, which will tell us what you decide to do. We will evaluate it for practicality, for interest, and for safety, give you feedback on that, and may ask you to modify your design based upon too easy, too hard. We're going to do machine vision, right? So that's too hard on this processor. Get port open CV. Yeah. So you're going to we'll attempt to act as the marketing department to tell you whether what you're specifying is interesting, and then as engineering consultants to tell you whether or not we think it's possible and doable. In general, for lectures, I would rather have you come and ask a lot of questions than stand up here and drone about code. That means it's a good idea to read about what's going to happen before it happens. But I have a general organizational question for you, and that is, for past years, I have attempted to give all the information for a lab before the lab starts. So for lab 2, I'll give all the information for lab 2 while you're doing lab 1. And as time goes on, people are less happy with that. Now my question to you is, when do you want to hear about a lab? Is it just-in-time learning? You find out about the lab on the day you're dropping into lab? Do you want to hear about it before the lab starts? What do you think? What is the phase relationship between the lectures and the lab? Should the lectures lead phase by 90 degrees or lag? Lag's probably a bad idea. Could be in phase, right? What do you think? Anybody? Nobody? Oh, come on, you have opinions.
Probably 3 to 4 days before.
3 to 4 days is one lecture.
Sure.
Is that what you mean? Lead by one lecture?
Make it 2.
Lead by 2 lectures. So get the introduction to the lab over with, but maybe not the lab details before it starts. This is what we're going to build. Here are the constraints. Here's some of the circuitry. And then drop into the code the same day you have to show us in lab? No. A little bit before that. What do you want? Because learning models are switching. You're different than the students 10 years ago. Not better or worse, just different. And so I want to try and match the presentation style to the learning model that you want to use. And if you want just in time, that has a couple of implications. One is you're going to read ahead and be ready to ask questions. But may be relevant because the model, the way I've done it in the past is at all times during the semester you're working on 3 different labs. There's the lab you're writing up that you're finished with, there's the lab that you're doing, and the lab you're hearing about. Some people complained about that, saying, well, too many different levels of abstraction all at once. What do you think? Yes?
So is it possible to start talking about Lab 3 after Lab 1 was already handed in?
So, you mean Lab 2?
Well, you said, we were all...
So the way I do it now is as soon as we start Lab 1, I get through Lab 1, I start talking about Lab 2. As soon as I get done with Lab 2, I start on Lab 3 before Lab 3 starts. Maybe in the first week of Lab 2, I start talking about Lab 3.
But at that point, was Lab 1 already done and forgotten with?
Done, it was done but not written up.
Right, so is it possible to start Lab 3 after Lab 1 has been written up and handed in?
I see. So that you're saying that wait until the first week of Lab 2 is done before starting on Lab 3 because Lab 1 is due the first week of Lab 2.
I'm not exactly sure how that would work, but...
That's an interesting idea. That actually makes sense because that cuts down the complexity to 2 items at a time rather than 3. That might be a reasonable compromise. Okay, I like that. Anything else? So split the difference. Don't start the next day on the new lab. Wait a week. Yeah? Anybody else? I'll go with that. I'm okay with that. All code examples I'm going to be talking about in class are going to be online. They're all online. That means you could bring a laptop and follow along. I don't have a problem with laptops in lecture. On the other hand, if you want to, you can take notes. Some people still do. Whatever works for you. Again, as soon as we're done here, and I have time to get a drink of water and check mail, I'm going to open up the lab for anybody. Who thinks they're going to build a board today? 1, 2, a few. But not too many. Okay, good. All right. So if 50 people had held up their hands, then we'd have to do something like have a schedule. But if there's 7 or 8 or 10, that'll probably work. Regarding the prerequisite, EC 3140, the primary concepts from 3140 that we're going to be assuming that you know are multitasking, interrupt service routines, how to write them and what they mean, what an I/O port is and how it works, although there's quirks for each different processor. This particular processor has input, output, pull up, pull down resistors, and it has a thing called peripheral pin select, which allows you to remap an I/O signal to a different pin on the fly. Oh dear. That sounds like a way to shoot your foot off. And it is. But it also gives you a lot of flexibility because there are something like 60 or 70 I/O signals and 27 pins, 28 pins. So several I/O signals could be mapped to the same pin, but you only get to choose one of them. So you may not be able to use every peripheral at the same time, but you can always find a pin that will map a peripheral. Actually, the way it works on this architecture is that many but not all of the I/O signals are mapped to an 8-way multiplexer and allows you to choose 8 different pins. It's cool, but you better read up on it. Concurrency and the issues that are involved with that's related to 3140. Assume that you know something about concurrent processes, how to coordinate concurrent processes. Prerequisites are merely suggestions. If you haven't taken a course, which is a prerequisite, I'm not going to kick you out of here. You might have to do some extra reading to figure it out, or do some extra thinking. But those are the main carryovers from 3140. If somebody wants more information on that was in that based on 3140, come talk, or send me an email, or shoot me a message on Piazza, or however you like. Course is lab oriented. There's 3 hours of lectures a week. It's a 4 credit class. You owe me 12 hours a week. That means I can ask for up to 9 hours a week in lab. Your lab section is 3 hours. You're going to have to figure out another way of getting 6 hours in lab. Lab's going to be open a lot. Lab is going to be open whenever I have free time. It'll be open Monday mornings, as early as you want to get here. If I opened up at 8 o'clock, would anybody be here? Okay, you're on. Otherwise, I would default to 9 because that tends to be the time that students start to ramble around. But I'll open up on Monday morning. I'll open up Tuesday morning. We cannot be in lab Monday afternoon or Tuesday afternoon because 2300 shares the room with us. EC 2300. And they think they have space in there on Monday and Tuesday afternoon. And late Monday night and Tuesday night. That means that the Tuesday night section, which goes from 4:30 to 7:30, is sandwiched between two EC 2300 sections, which means you cannot come early and you cannot stay late. Shared space. You're going to spend a lot of time in the lab, folks. Yeah.
Does all of our work have to be done in lab?
Not all the work has to be done in lab. You have an oscilloscope at home?
Yeah.
Sweet. You're on. I didn't expect that answer, but I'm not too surprised. I'm really not too surprised. If you oscilloscopes are actually quite cheap now. You can buy an oscilloscope which is good enough for this course for about probably less than $50. And if you go out to eBay, you can get even a good Tektronix for $100. It's cheaper than a textbook. But we're going to keep the lab open enough that you can get your work done. If you want to work at home, you're going to need to buy a power supply for the board. You can build a board and take it with you, but you can't take the power supply, because I have 100 boards you can build, but I only have 50 power supplies. People start taking them home. You know where they'll all be? At home. Because power supplies are invisible, folks. Once you plug them in, you can't see them anymore. Tell me I'm wrong. I harvest between 20 and 30 cell phone chargers a year out of the lab. Nobody ever comes back for them because they're invisible. And so you can't take them home. You can't take the power supplies out of the lab. The weirdest things disappear. We lost 40 wire strippers last year. Who the hell steals a wire stripper? Nobody. Where are they? I don't know. Joe's lab? Al Molner's lab? I don't know. We should be wading through them, right? I mean, anyways. So, yes, you can work at home. You can certainly program at home. You have the target board. You could, of course, for 10 minutes work, wire a 9-volt battery to run your board and skip the power supply, skip the 110-volt power supply. I have the mating plugs to plug 9-volt batteries into your target boards. That gives you a completely standalone system. You can program that directly off of your laptop. All you need then is a way of powering the peripherals, if any. You have a logic analyzer at home?
Yeah.
Oh my God.
It's actually a 2-in-1. It's pretty pretty.
It's good. I have an oscilloscope at home, which I got off the loading dock. They were going to throw it out. It's that deep. It's got a cathode ray tube in it. It's really primitive. But the price was right. Okay. What else? Any last minute questions here about logistics? Yes?
Are you allowed to work in other people's lab sections?
If there is an open seat, you're welcome to come in and work. So Tuesday can come into Wednesday. Wednesday afternoon I'll be in lab, but there's no scheduled section Wednesday afternoon. I come in there and sit in lab waiting for somebody to appear, because people need extra time. You're welcome to come in anytime there's staff in the lab. Now, if the lab section is full and you can't find a seat, yeah, okay. You could still work in the lab, you'll just have to work at one of the soldering stations. Unless people are soldering. Yes?
I noticed that this course's piazza is the same piazza from last year.
It is, well, yes.
I remade it. So this is good in that when you search things, the results from last year will come up, but the problem is you can't tell what's still correct and what has changed since last year. So if I
You can by the date. You want me to delete the post from last year?
Most courses make a new piazza every year.
Nah, screw that. Nope, sort by date, or keep up with it. I don't see a strong reason to do that. How do other people feel though? Let me ask you, how do people feel? Is this a real problem that you'd like a fresh piazza? Because there is actually some useful information from last year. Yes? Fresh?
Well, maybe for organizational purposes.
Moldy? Fresh? So what if, let's see if I can figure out some way of tagging the stuff as being deprecated. Let me see if I can do that. Maybe that's a good compromise. Because really, most of the things that were considered last year are going to be relevant this year. There's detailed changes in the labs, but not huge changes. Same processor. The labs are, the process here is that the lab should teach you the same thing, but they should be different enough that code is not useful from last year. So it's really the same labs, but with different endpoints so that it's not quite usable. Yes?
Do we have maybe a separate Piazza page for like new stuff, and then we can just like look and feel it?
Oh God, I don't. Let me think. Let me see. Let me see what the mechanism is for aging on Piazza. I don't. Okay, I hear you. So, is there a general feeling that having 2 years at Piazza is a burden? Yes.
I mean,
No.
You just tag things like Lab 1, 2017.
They're all tagged.
I know, but like.
Oh, you'd like a year tag on it too.
Why not? Just do that.
That I could do. That's easy to do. So I just need a new category on there saying 2017. I can. Would that do it for you if I tagged them as 2017?
Could you change all of the things that are tagged previously? So currently
No.
you have things tagged lab 1, lab 2, lab 3, lab 4. Can you change that to have a year inside that tag?
I doubt it. Retrospectively, I don't. I'll look at the Piazza mechanism, or the pizza mechanism, and see what I can do. That makes the information available but deprecated. Okay. All right. I will see you Friday with high probability.